Question 2 on electricity. We have a 75 watt non-inductive filament light bulb, and the non-inductive part means that despite all of the small coils of wire wound up in the filament, that it's not an inductor, even though an inductor is a coil of wire, so we don't need to worry about that part of it. So this non-inductive filament light bulb is designed to run from an AC supply of 120 volts RMS. That's also important, so I'll circle that, and 50 Hz. The only supply available is 240 volts RMS and 50 Hz. So frequency is the same, voltage doubled. A is calculate the resistance R that would have to be placed in series with the bulb so that the bulb could run at the correct power, and calculate the resultant power drawn from the supply. There's two things. We're trying to find both R and the power drawn from the supply. So it makes sense that if this is our, well, it's a DC circuit, if this is our circuit here with our light bulb and our resistor, that we should have 120 volts across each. So that means, where are we? That means the effective resistance R of the light bulb is going to be the same as R that we're trying to calculate. So we'll put it this way: we don't know the resistance. We know what the power of that resistor will be, because it has to be the same as for the light bulb, because it has the same current running through it, and it has to be equal to the resistance of the light bulb when it's operating. So the power is going to be 75 watts. That incidentally answers the second part of the question. It's going to be 150 watts, 75 over each of those components. We know the voltage, because voltage has to be 120 volts RMS. And I believe that gives us enough information to work out the resistance. We have the power formula, P equals IV, and we can use Ohm's law to remove the current from the equation so that we don't have to deal with that. And I equals V over R, so P equals V squared over R. And we can rearrange this to find the value of R. So that would mean R equals, where are we, V squared over P, which means 120 squared divided by 75 watts. And that gives you about 192 ohms. So B, we've got the resistance replaced, this time with an ideal inductor. We have to calculate the inductance that must be used so that the bulb can operate at the correct power, and calculate the resultant power. So same thing as the question above, except this time we're calculating the inductance and the power from the supply. Okay, just change colour so that it's a little bit clearer. Now this is going to involve phasors. We've got the voltage over the inductor, because remember we're in our AC supply. We've got the voltage across the resistance, and I noticed I've drawn the inductance phasor, the voltage phasor for the inductor, vertically upwards rather than downwards. This is because your phasors rotate in this direction, and your inductance leads the voltage across the resistance. Now what this means is when these two combine, it's going to produce a supply voltage here, Vs. And we know that the supply voltage is 240 volts RMS. We know that the resistance voltage has to be 120 volts RMS, so that tells us we can calculate what VL will be. It's going to be 240 squared minus 120 squared, square root all of that. And that works out approximately 200 volts, but yeah, you can work out a little over 200. So, how does that help us? That gives us one really important piece of information for calculating a little bit later. Remember, we're aiming for L, and the equation for which has L involved in it, which is where we need to end up, is our reactance of the inductor equals 2 pi FL. We know the frequency. If we can find XL, we can find L. So I'll just work backwards through this. This is why I'm going for the voltage. But working backwards through it, if we use Ohm's law for the reactance of the inductor, we've got V across the inductor equals I times XL. There's XL instead of R. So we don't know the current, but we can work out the current, and we do know the voltage. The current I equals V over R when we're dealing with the voltage of the resistor and the value of the resistance, because we just calculated that above. So the voltage across the resistor is 120 volts. The value of the resistance is 192 ohms. Now it's really important to note that these are not going to be the same. So the current will be the same for the inductor because it's passing through both the resistor and the inductor, but the voltage will be different, as we can see from our phasor diagram over here. The voltage across the inductor is different. It's around about 200 volts. So it's not 120 volts like it is for the resistor. So we are going to have a different value of reactance. The reactance will definitely be different compared to the resistance. There's a lot of elements to draw in here. It's worth watching this through a couple of times and trying it yourself afterwards again. But in any case, we take this value of the current and we substitute that in there. We take the value of the voltage, we substitute that in there, and we rearrange to find XL. Once we've got XL, we can then rearrange to find L over here. And you can do that on your own. This is mostly concerned with the process. But the power now, so that deals with L. The resultant power, this one is actually easy when you understand that the inductor itself does not cause any extra supply voltage to be drawn. The idea of reactance is that it's reacting to what's already in the circuit. It's not a reaction is a secondary event. The primary event is the power supply in the resistor, which is operating in that kind of initial, if you like, controlling phase direction. Or, I don't know. So any put it this way, any power that the inductor draws, it will return to the circuit. So the inductor, and remember it's an ideal inductor, so anything it takes from the circuit it returns. So and an ideal inductor is 100% efficient as well. So you don't lose any energy through heat in the resistance of it, and the internal resistance. I think later on it talks. There's a question to do with that, but yeah. So what is the power going to be? It's going to be 75 watts. Exactly the same. So it's a more efficient circuit than if you have a resistor in place.